Why can nothing travel faster than the speed of light? This question is not just a scientific curiosity. It is the key to understanding why time exists, why space has 3 dimensions, and why you and I exist at this precise moment. What you will discover in the next 90 minutes will forever change the way you perceive reality. Imagine you're driving on a highway and you see a sign that reads, "Maximum speed, 120 kilometers per hour." You know it is a rule, an arbitrary human law. But now, imagine you reach the end of the universe and see a sign that reads, "Maximum speed, 299,792 kilometers per second." This is not an arbitrary rule. It is the most fundamental law of physics. And unlike human laws, you cannot break it, not even a little bit. For centuries, physicists believed that the universe had no speed limit, thinking that with enough energy, you could accelerate anything to infinite speeds, and traveling to another galaxy would simply be a matter of having a powerful enough engine. But in 1905, an unknown 26-year-old clerk in a Swiss patent office wrote a paper that destroyed that idea forever. Albert Einstein proposed something radical. The speed of light is always constant for everyone, regardless of whether you are moving toward the light or away from it, and regardless of whether the light comes from a moving star or a static lamp, the speed will always be the same, approximately 300,000 kilometers per second. This sounds simple, almost trivial, but the consequences of this assertion are so profound, so unsettling, that even today, more than 100 years later, we still struggle to fully comprehend them. Because if the speed of light is always constant, then something else must change, and that something is time and space. Your time is not my time. Your space is not my space. Simultaneity does not exist. The present is an illusion, and all this happens because a cosmic speed limit exists. But here is the part that no one tells you. That limit is not really about light. The light is just the messenger. The real limit is about information, causality, and the speed at which the universe can process events. C does not mean celerity. It means causality. It is the speed of space-time itself. And do you know what the strangest thing of all is? That specific number, 299,792,458 meters per second, is not arbitrary. It emerges from the electromagnetic properties of a vacuum. It is woven into the very structure of reality. If it were different, even slightly, atoms could not exist, stars would not form, the universe would be a chaos of meaningless particles, and you would not be here to wonder why. In this documentary, we are going to unravel one of the deepest mysteries in physics. I will not just explain why nothing can go faster than light. I will reveal what C truly is, why the universe chose that specific number, and how this seemingly restrictive limit is, paradoxically, what allows everything we know to exist. We will explore the experiments that changed our understanding of the cosmos. We will unmask the apparent exceptions that seem to break the rules. We will immerse ourselves in the hidden geometry of space-time, and, in the end, I will reveal something you probably never imagined, that you, right now, as you listen to this, are traveling at the speed of light, only not through space, but through time. If you have ever wondered why the universe is the way it is, why you cannot travel to the past, why the stars are far away, why we age, or why causality exists, the answer lies in that number, 300,000 kilometers per second, a limit that is not a restriction, but the very condition of existence. And if this journey through the limits of the universe fascinates you as much as it fascinates me, I invite you to subscribe to Scientia Nocturna. Here we explore the deepest mysteries of the cosmos, those that keep you awake at night, wondering about the nature of reality. Because the best answers are not the ones that quench your curiosity, but the ones that ignite it even more. So, prepare yourself, because what you are about to discover is not just science, it is a revelation about the very nature of existence. And once you understand it, you will never see the universe the same way again. let us begin. Why can nothing travel faster than the speed of light? To answer this question, we first need to understand what exactly that magical number is. 300,000 kilometers per second. Where does it come from? Who measured it first? And why is it precisely that value and not another? The history begins long before Einstein, in the 17th century, when most scientists were not even sure that light had a speed, many believing that light traveled instantaneously, that when you light a candle, the light reaches your eyes at the very same instant, without any delay. It seemed reasonable. After all, we never notice any lag when we look at something. But in 1676, a Danish astronomer named Oumuamua made an extraordinary discovery while observing Jupiter's moons. Oumuamua noticed something strange. Jupiter's moons seemed to orbit faster when the Earth was approaching Jupiter, and slower when the Earth was moving away. But that made no sense. The moon's orbits should be constant. Oumuamua had a brilliant idea. The moons were not changing their orbital speed. What was changing was the time it took for the light to travel from Jupiter to Earth. When the Earth moved away from Jupiter, the light had to travel a greater distance, so the moons appeared to be delayed. When the Earth approached, the distance was shorter, so the moons appeared to be ahead of schedule. With this observation, Oumuamua calculated that light traveled at approximately 220,000 kilometers per second. It was not exact, but it was the first real calculation of the speed of light. And it proved something revolutionary. Light does not travel instantaneously. It has a finite speed. For the next 200 years, scientists worldwide tried to measure the speed of light with greater precision. In 1849, the French physicist Hippolyte Fizeau used an ingenious experiment with a spinning toothed wheel and a mirror placed several kilometers away. He made a beam of light pass between the teeth of the wheel, travel to the mirror, return, and, if the wheel had spun enough, the beam would be blocked by the next tooth. By measuring the wheel's rotation speed, Fizeau calculated that light traveled at approximately 313,000 kilometers per second. Closer, but still not exact. Then came Léon Foucault, who improved the method using rotating mirrors. Then Albert Michelson, who dedicated decades of his life to perfecting the measurements. And, with each experiment, the number got closer and closer to what we now know as the exact value. 299,792,458 meters per second in a vacuum. But here is the question no one was asking at the time. Why that number? Why not 500,000 kilometers per second, or 100,000, or 1 million? What is so special about exactly 300,000 kilometers per second? For most scientists of the 19th century, the speed of light was simply an interesting property of light, like its color or its ability to reflect off mirrors. They thought it was just a characteristic of the medium through which the light traveled, the luminiferous ether, an invisible substance that supposedly filled all space. But there was a problem with the ether, a huge problem, and that problem would lead to the most important experiment in the history of physics. In 1887, two American scientists, Albert Michelson and Edward Morley, decided to measure the Earth's velocity through the ether. They reasoned like this: if the Earth is moving through the ether, then light should travel faster when it goes in the direction of the Earth's motion, and slower when it goes against it. It is like swimming in a river. You swim faster with the current and slower against it. They built an incredibly sensitive instrument called an interferometer. They split a beam of light into two, sent each half in perpendicular directions, bounced them off mirrors, and recombined them. If the light traveled at different speeds in different directions, the beams would arrive slightly out of phase and create an interference pattern. Michelson and Morley expected to see that pattern. The entire scientific community expected to see it. It was the final confirmation of the ether theory. But they saw nothing, absolutely nothing. No matter which direction they pointed the instrument, no matter the time of day or the time of year, the light always traveled at the same speed, exactly the same, in all directions, all the time. This negative result was one of the most important discoveries in the history of science, because if light always travels at the same speed, regardless of the observer's motion, then the ether does not exist. Then we need a completely new explanation for light. But there was something more, something much deeper and more unsettling in that result. If the speed of light is always constant, independently of the observer's motion, then our understanding of space and time must be fundamentally wrong. Think of it this way. Imagine you are on a train traveling at 100 kilometers per hour, and you throw a ball forward at 20 kilometers per hour from your perspective. For someone standing outside the train, the ball travels at 120 kilometers per hour, the speed of the train plus the speed of the ball. That is common sense. That is what Newton taught us. But now, imagine that instead of throwing a ball, you turn on a flashlight. The light leaves the flashlight at 300,000 kilometers per second from your perspective. How fast does the light travel for someone standing outside the train? According to Newton, it should be 300,000 kilometers per second, plus the speed of the train. But the Michelson-Morley experiment proved that it is not. The light travels at 300,000 kilometers per second, always. For you on the train, for the person outside, for everyone. The speeds do not add up. This is impossible, according to classical physics. It is as if mathematics itself is broken. It is as if the universe were cheating. And that is when Einstein appears. In 1905, Einstein did not have access to sophisticated laboratories. He did not have research funding. He was just a 26-year-old clerk in a patent office. But he had something more powerful, a thought experiment. Einstein asked himself, what would happen if the speed of light were really constant? Not because the ether made it constant, but because that is a fundamental law of the universe. What would have to be different in our physics for that to work? And he came to a devastating conclusion. If the speed of light is constant, then time and space cannot be constant. They must be relative. They must change depending on how fast you move. This meant that your clock and my clock do not tick at the same time, that your meter stick and my meter stick do not measure the same distance, that there is no universal now that we all share. Time is different for every observer. Space is different for every observer. Einstein called this the theory of special relativity, and at its heart was that number, 300,000 kilometers per second, not as the speed of a thing called light, but as a fundamental constant of the universe, a speed that nothing can surpass because it is the speed of space-time itself. But the question remains, why that specific number? Why did the universe choose exactly 299,792,458 meters per second? The answer, as we will see in the next chapters, is even stranger than Einstein imagined, because that number was not chosen arbitrarily. It emerges mathematically from the electromagnetic properties of the vacuum. It is encoded in the structure of space-time, and if it were different, even by an infinitesimal fraction, the universe as we know it could not exist. We have only just begun to unravel the mystery, and every answer leads us to even deeper questions. The Michelson-Morley experiment of 1887 is, without exaggeration, the most successful failed experiment in the history of science. They tried to prove the existence of the luminiferous ether and failed, but that failure destroyed centuries of certainties and opened the door to a new physics that would forever change our understanding of the universe. To understand why this experiment was so revolutionary, we first need to understand what the ether was and why all 19th century scientists were convinced it existed. For centuries, physicists had observed that waves need a medium to propagate. Water waves need water, sound waves need air, or some other material. You cannot have waves without something that waves. And light, as Thomas Young demonstrated in his famous interference experiments, clearly behaved like a wave. It could diffract, reflect, and create interference patterns. It was, undoubtedly, a wave. But there was a problem. Light travels through the vacuum of space. It travels from the sun to the earth, across millions of kilometers of nothing. So, what is waving? What medium is carrying those light waves? The obvious answer, scientists thought, was that space was not really empty. It had to be filled with an invisible, imponderable, massless, but absolutely real substance: the luminiferous ether. This ether permeated everything. It filled the space between stars, passed through planets. It was in this room with you right now, and it was the medium through which light traveled. Exactly as air is the medium through which sound travels. But if the ether existed, then it should have measurable consequences. The most obvious was this: if the Earth moves through the ether as it orbits the Sun at approximately 30 kilometers per second, then we should feel an ether wind, exactly as you feel the wind when you drive a car with the window open. And that ether wind would affect the speed of light. When light travels in the direction of the Earth's motion through the ether, it should travel faster. When it travels against the motion, it should travel slower. And when it travels perpendicular to the motion, it should be somewhere in between. Albert Michelson, a brilliant experimental physicist, and Edward Morley, a meticulous chemist, decided to measure this effect. To do so, they built what is now known as the Michelson-Morley interferometer, one of the most elegant and ingenious instruments in the history of experimental physics. The design was simple, yet powerful. They took a beam of light and split it in two, using a half-silvered mirror. One beam traveled to the north, bounced off a mirror, and returned. The other beam traveled to the east, bounced off another mirror, and also returned. Then, they recombined the two beams. If both beams traveled at the same speed, they would arrive at the same time and combine perfectly. But if one traveled faster than the other, even by an infinitesimal fraction, they would arrive slightly out of phase. And that phase shift would create a pattern of interference, fringes, alternating bands of light and darkness that Michelson and Morley could observe and measure. The expectation was clear. If the Earth moves through the ether, then the beam traveling in the direction of the Earth's motion should be affected by the ether wind, while the perpendicular beam would be affected differently. The interference fringes should change as they rotated the apparatus. Michelson and Morley mounted their interferometer on a stone slab floating in mercury to eliminate any vibration. They placed it in a basement to prevent temperature changes. They isolated it from everything possible, and then, with unprecedented precision, they began to measure. They rotated the apparatus, observed it at different times of the day, used it at different times of the year, when the Earth was moving in different directions around the Sun. They made adjustment after adjustment, measurement after measurement, and they found nothing. Absolutely nothing. The interference fringes did not change, no matter the direction, no matter the time, no matter the time of year. The two light beams always arrived at exactly the same time. The light traveled at the same speed in all directions. Michelson was devastated. He had built the most precise instrument of his time, specifically to detect the Earth's motion through the ether, and he had failed. He considered the experiment a total failure. Years later, when he received the Nobel Prize for his experimental work in optics, he still felt he had disappointed the scientific community. But the scientific community was equally perplexed. How was it possible that they did not detect the ether? Some proposed that perhaps the Earth dragged the ether with it, like a ship dragging water, but that contradicted other astronomical observations. Others suggested that perhaps objects contracted in the direction of motion through the ether, exactly cancelling the effect Michelson and Morley were trying to measure. This was the Lorentz-Fitzgerald contraction theory, and although it worked mathematically, it seemed like an ad hoc solution, a convenient explanation without deep justification. The truth was much more radical, and that truth would not come from new experiments or better instruments. It would come from rethinking the most basic assumptions about the nature of space and time. What Michelson and Morley had discovered, without realizing it, was that the speed of light is invariant. It is the same for all observers, no matter how they move. It does not add or subtract. It does not depend on the motion of the source, or the motion of the detector. It is a fundamental constant of the universe. But if the speed is constant, then something else must change, and that something is time and space. Think of it this way. Imagine you are driving a car and you measure how fast you move. Speed is distance divided by time, kilometers per hour. If the speed of light is always constant, but the observer can be moving, then for the equation to work, the distance measured by one observer and the time measured by another must be different. Your meter is not my meter. Your second is not my second. Space and time are relative. This was the implication of the Michelson-Morley experiment, and although they never saw it, others did. The Dutch mathematician Hendrik Lorentz developed the mathematical transformations that described how measurements of space and time change when you move. The French physicist Henri Poincaré explored the philosophical implications of a universe without ether, but it was Albert Einstein who took the final and most radical step. Einstein did not just accept that the speed of light was constant. He made that a fundamental postulate, a law of nature, and built an entire new physics around that idea. In his 1905 paper on the electrodynamics of moving bodies, Einstein began with two simple principles. First, the laws of physics are the same for all observers, moving at a constant velocity. Second, the speed of light in a vacuum is the same for all observers, regardless of the motion of the light source or the observer. From these two apparently innocent principles, Einstein derived extraordinary consequences. Time dilates, moving clocks run slower, space contracts, moving objects shorten in the direction of motion. Mass increases, moving objects become heavier, and simultaneity is relative. Events that are simultaneous for one observer are not for another. All this happens because the speed of light is constant. The Michelson-Morley experiment had tried to prove the existence of the ether and had failed. But in failing, it had revealed something much deeper. That the universe does not operate according to the rules of common sense. That space and time are not the fixed and immutable stage on which events occur. They are part of the show. They are flexible, malleable, relative. And all this was coded in that number, 300,000 kilometers per second, not as a property of light, but as a property of the universe itself. Michelson never fully accepted Einstein's relativity. Until the end of his life, he kept hoping that someday the ether would be found. He died in 1931, without knowing that his failure had been the foundation of modern physics. Because the Michelson-Morley experiment did not prove that the ether did not exist. It proved something much more radical, that space and time themselves are dynamic, that the speed of light is not a limit imposed from outside, but an intrinsic property of the fabric of space-time. And that leads us to the deepest question of all. What exactly is c? Is it really the speed of light? Or is it something more fundamental? The answer, as we will see in the next chapter, will completely change your understanding of what speed, time, and causality mean. In 1905, Albert Einstein was 26 years old and worked 6 days a week evaluating patent applications in Bern, Switzerland. He did not have access to sophisticated laboratories. He did not have colleagues with whom to discuss theoretical physics. He did not have research funding. In fact, he did not even have a university position. His application to be an assistant professor had been rejected, but he had something no laboratory could provide: a mind capable of seeing beyond appearances, of questioning the most basic assumptions, of performing experiments in his imagination that would reveal truths about the universe that no instrument could measure. And in that extraordinary year, while working in a patent office during the day and thinking about physics at night, Einstein published 4 papers that would change science forever. One explained the photoelectric effect and laid the groundwork for quantum mechanics. Another proved the existence of atoms. A third developed the theory of Brownian motion. But the 4th paper, titled On the Electrodynamics of Moving Bodies, was the one that would shatter our notions of space and time. It was the theory of special relativity. And it all started with a simple question: that Einstein had asked himself since he was 16. What would you see if you could travel alongside a beam of light? Imagine you are running alongside a light wave, traveling at exactly the same speed as it, 300,000 kilometers per second. According to Newton's classical physics, you should see the light wave frozen in space, motionless, as if you were standing next to an ocean wave that miraculously does not move. You would see an electric and magnetic field oscillating in space, but not propagating. But Einstein knew this was impossible. James Clerk, Maxwell's equations of electromagnetism, developed in the 1860s, did not allow for stationary electromagnetic waves of this type. If Maxwell's equations were correct, and all experiments suggested they were, then you could not reach the speed of light. You could not see a frozen light wave. This paradox obsessed him for 10 years, and finally, in 1905, he had his moment of revelation, not while working on complex mathematical equations, but during a casual conversation with his friend, Michele Besso, as they walked home from the patent office. Einstein realized that the problem was not in Maxwell's equations. The problem was in the assumptions about time. He had assumed, like everyone else, that time was universal, that a cosmic clock existed that ticked the same time for everyone in the universe. But what if that was false? What if time was different for observers in motion? The next day, Einstein returned to Besso and told him, "Thank you. I have completely solved the problem." In the following weeks, he wrote his paper on special relativity, a work that cited no bibliographic references because it was not based on other works. It was based on pure thought, on thought experiments, on rethinking the most fundamental assumptions about reality. The article began with two incredibly simple postulates, so simple they seemed almost trivial, but their consequences were devastating. The first postulate was the principle of relativity. The laws of physics are the same for all observers, moving at a constant velocity. If you are on a smoothly moving train at a constant velocity without looking out the window, you cannot perform any physical experiment that tells you you are in motion. Physics is the same for you as for someone standing at the station. This was not really new. Galileo had proposed something similar 300 years earlier. But the second postulate was revolutionary. The second postulate was the invariance of the speed of light. The speed of light in a vacuum is the same for all observers, regardless of the motion of the light source or the observer. If you are standing still and measure the speed of light, you get 300,000 kilometers per second. If you are in a spaceship traveling at 99% of the speed of light and measure the speed of a light ray passing you, you still get 300,000 kilometers per second. You do not get 300,000 kilometers per second plus 99% of 300,000. You get exactly 300,000. This completely contradicts our intuition about how velocities work. If you are in a car going at 100 kilometers per hour and you throw a ball forward at 20 kilometers per hour, the ball travels at 120 kilometers per hour relative to the ground. Velocities add up. That is Galilean velocity addition, and it works perfectly for everyday objects, but it does not work for light. The speed of light does not add up. It is always constant. How can this be possible? The only way is if time and space are not constant. If they adjust, if they deform, if they change in such a way that the speed of light remains always the same. Einstein derived the exact mathematics of how this works. He used the Lorentz transformations, which Hendrik Lorentz had developed years earlier, to explain the result of the Michelson-Morley experiment. But he gave them a completely new meaning. For Lorentz, they were just mathematical tricks, effects of the ether. For Einstein, they were the fundamental reality of spacetime. The consequences were extraordinary. First was time dilation. If you travel very fast, your clock runs slower compared to a stationary clock. It is not that your clock is broken. It is that time itself slows down for you. If you travel in a spaceship at 90% of the speed of light for what is 1 year to you, when you return to Earth, more than 2 years will have passed, your time dilated. This is not science fiction. It is a fact measured experimentally thousands of times. Subatomic particles called muons, created by cosmic rays in the upper atmosphere, live only 2 microseconds before decaying. At their speed, they should travel only 600 meters before disappearing. But we detect them on the Earth's surface after they have traveled more than 10 kilometers. How? Because they are traveling so fast that their time dilates. For them, they have only lived 2 microseconds. But for us, they have lived much longer. Atomic clocks on GPS satellites experience time dilation. They run slightly faster than clocks on Earth because they are moving faster and because they are in a weaker gravitational field. If we did not correct for relativity, GPS would be useless. It would accumulate errors of kilometers in a matter of minutes. Then there was length contraction. Moving objects shorten in the direction of motion. It is not an optical illusion. It is not that they look shorter, they are actually shorter. If a 100-meter-long spaceship travels at 90% of the speed of light, from your perspective, it measures only 44 meters. For someone inside the ship, it still measures 100 meters. Both measurements are correct. Length is relative. After that was the relativistic mass increase. The faster an object moves, the heavier it becomes. It does not gain additional atoms, but its inertial mass, its resistance to acceleration, increases. As you approach the speed of light, your mass approaches infinity. That is why you cannot reach the speed of light if you have mass. You would require infinite energy to accelerate an infinite mass. And finally, the strangest of all, the relativity of simultaneity. Events that are simultaneous for one observer are not for another in motion. There is no universal now. The present is not an objective reality shared by everyone. It is relative to your frame of reference. Imagine you are in the center of a moving train car, and 2 lightning bolts simultaneously strike the ends of the car. You see them at the same time because you are exactly in the middle. For you, they were simultaneous. But for someone standing on the platform watching the train pass, the bolt at the back occurred first, because the train is moving toward the front bolt, shortening the distance the light has to travel. For them, they were not simultaneous. Who is right? Both. There is no single correct answer. Simultaneity is relative. These are not approximations. They are not small effects that only matter at extreme velocities. They are the fundamental nature of reality. It is just that in our daily lives, we move so slowly compared to the speed of light that the effects are imperceptible. But they are there. They have always been there. Einstein had taken the negative result of the Michelson-Morley experiment, the strange fact that the speed of light was always constant, and had built a new physics around it, a physics where space and time were malleable, where mass and energy were interchangeable, where causality itself had a speed limit, and all this was contained in that number, 300,000 kilometers per second, not as the speed of something moving through space, but as the speed of space-time itself. It was the speed at which causality propagates. It was the maximum speed of information in the universe. But Einstein did not stop there. In that same paper, almost as an afterthought, he derived the most famous equation in physics, E equals mc squared. Energy equals mass, multiplied by the speed of light squared. This simple equation said something profound. Mass and energy are the same thing. Mass is frozen energy. Energy is mass unleashed, and the conversion between them is mediated by c squared, the speed of light squared. That c there is not accidental. It is not there just because light is fast. It is there because c is the fundamental constant that relates space to time, that relates mass to energy, that defines the very structure of space-time. The reaction to special relativity was mixed. Some physicists, like Max Planck, accepted it immediately. Others, including many of the most prominent of the time, rejected it. Henri Poincaré, who had been close to developing relativity himself, never gave Einstein full credit. Hendrik Lorentz never completely abandoned the idea of the ether, but the experimental evidence quickly accumulated. Every prediction of special relativity was confirmed. Time dilation, length contraction, or mass increase, E equals mc squared. Everything was correct. And 10 years later, in 1915, Einstein extended his theory to include acceleration and gravity. General relativity described how mass curves space-time, how gravity is not a force, but a curvature of space itself. And again, c was at the center of everything, as the maximum speed of gravitational waves, as the constant that relates the curvature of space-time to the distribution of mass and energy. But even then, even with all the experimental confirmation, Einstein himself struggled with the philosophical implications. He had shown that time was relative, that simultaneity was an illusion, that the now had no absolute meaning. Years later, when his friend Michele Besso died, Einstein wrote to Besso's family, "Now he has departed from this strange world, a little ahead of me. That means nothing." For us convinced physicists, the distinction between past, present, and future is only an illusion, however persistent. The relativistic revolution was not just about physics. It was about the nature of reality itself, and it had all begun with a simple question about the speed of light. There is one question we all ask when we first hear about the speed limit of light. Why can you not just keep accelerating if you have a powerful enough rocket, a strong enough engine? Why couldn't you eventually reach 300,000 kilometers per second and then surpass it? The answer is not technical. It is not that our rockets are not good enough. It is not that we do not have the technology. It is that the universe itself forbids it. And the reason is in the most famous equation in physics, E equals mc squared. This simple equation of three symbols contains a truth so profound about the nature of reality that even more than 100 years after Einstein wrote it, we are still discovering its implications, and at the heart of that equation is the answer to why nothing with mass can travel at the speed of light. Before Einstein, physicists thought that mass and energy were completely different things. Mass was the amount of matter in an object. Energy was the capacity to do work, to move things, to heat things. They were separate categories, different quantities, measured in different units, but Einstein showed that they were wrong. Mass and energy are not different things. They are the same thing. Mass is simply highly concentrated energy. Energy is mass unleashed, and the conversion constant between them is c squared, the speed of light squared. What does this really mean? It means that every piece of mass contains an extraordinary amount of energy, because c squared is an enormous number. The speed of light is 300 million meters per second. Squared, it is 90 quadrillion meters squared per second squared. That means that a single kilogram of mass contains 90 quadrillion joules of energy. To put that in perspective, the energy contained in 1 kilogram of matter is equivalent to the energy released by 25 megatons of TNT. That is enough energy to power a country the size of the United States for several days, all contained in 1 kilogram of ordinary matter. Of course, we usually cannot release all that energy. In chemical reactions, like burning gasoline, we only convert approximately 1 billionth of the mass into energy. In nuclear reactions, like in the sun or in atomic bombs, we convert around 1%. Only in matter, antimatter annihilation, when an electron meets a positron, is 100% of the mass converted into energy. But the equation, E equals mc squared, is not just about converting mass into energy. It is about the fundamental nature of mass itself, and this is where it connects to the speed limit of light. When you accelerate an object, you are adding energy to it, kinetic energy, the energy of motion. In Newtonian physics, this kinetic energy is simply 1/2 of the mass multiplied by the velocity squared. Double the speed, and you quadruple the energy. Simple. But in Einstein's relativity, something strange happens. When you accelerate an object, not only does its velocity increase, but its mass also increases. Not its rest mass, the amount of matter it has, but its relativistic mass, its resistance to acceleration, at low speeds, this effect is imperceptible. If you drive your car at 100 kilometers per hour, your relativistic mass increases by approximately 1 part in 1 quadrillion. It is so small that no instrument could measure it. But as you approach the speed of light, the effect becomes dramatic. At 50% of the speed of light, your mass increases by approximately 15%. At 90%, your mass more than doubles. At 99%, your mass is 7 times greater than your rest mass. And as you get closer and closer to the speed of light, your mass approaches infinity. This creates a fundamental problem. To accelerate an object, you need to apply a force. That force adds energy. But that energy does not only increase the object's speed, it also increases its mass. And the more mass the object has, the more energy you need to accelerate it further. It is a vicious cycle. At speeds close to light, every time you want to increase your speed, even a little, you need to add exponentially greater amounts of energy. And that energy is converted into more mass, which makes it even harder to accelerate. When you reach exactly the speed of light, your mass becomes infinite. And to accelerate an infinite mass, you would need infinite energy. Not just a lot of energy, not just more energy than exists in the universe, but literally infinite energy. This is not a technological limitation. It is not that we do not have enough fuel, or that our engines are not powerful enough. It is a fundamental mathematical impossibility. It is like asking, how much money do I need to buy the largest number? There is no answer. The largest number does not exist. Similarly, there is no amount of energy that can accelerate an object with mass up to the speed of light. So, why can light travel at the speed of light? The answer is surprisingly simple. Because light has no mass, or more precisely, photons. The particles of light have zero rest mass. If an object has zero rest mass, then the equations of relativity give it only 2 options: to be at rest, or to move at exactly the speed of light. There is no middle ground. A photon is never at rest. From the moment it is created until the moment it is absorbed, it travels at 300,000 kilometers per second, always, without exception. This creates a strange situation. From the photon's perspective, if we can even speak of such a thing, time does not elapse. In its frame of reference, the universe is completely contracted in the direction of its motion. It is emitted and absorbed in the same instant. It experiences neither time nor distance. But there are other massless particles besides photons. Gluons, which transmit the strong nuclear force, are massless. Gravitons, if they exist, the hypothetical particles that transmit gravity, would also be massless. All these particles travel at c, the speed of light. In fact, c is not really the speed of light. It is the speed of all massless particles. It is the speed of causality itself. Light just happens to be the most familiar manifestation of this fundamental speed. But here is the really fascinating part. Technically, everything is composed of fundamental particles, and most of those particles get their mass from a quantum field called the Higgs field. Before interacting with the Higgs field, all fundamental particles would be massless and would travel at the speed of light. The Higgs field, finally discovered at the Large Hadron Collider in 2012, permeates all of space. When particles move through it, they interact with it, and that interaction gives them mass. It is like swimming through molasses. The molasses does not make you heavier in the sense of adding more matter, but it makes it harder to accelerate, which is effectively the same as having more mass. Electrons interact strongly with the Higgs field, which is why they have a relatively large mass for fundamental particles. Quarks do too. Neutrinos interact very weakly, which is why they have very small masses, and photons do not interact at all, which is why they are massless and travel at c. So, in a sense, the question, why can I not travel at the speed of light, can be answered like this: because you are made of particles that interact with the Higgs field, and that interaction gives you mass, and having mass means you cannot reach c. But there is another way to think about this, an even more profound way. In relativity, velocity is not just how fast you move through space, it is how fast you move through space-time, that four-dimensional construct that combines the three dimensions of space with the single dimension of time. And here is the secret. Everything moves through space-time at exactly the same speed, which is c, the speed of light. When you are at rest, you are not moving through space, but you are moving through time at maximum velocity. You are traveling into the future at 1 second per second. All your velocity is in the temporal direction. When you start moving through space, some of your velocity through time is converted into velocity through space. You move slower through time and faster through space. That is time dilation. If you could reach the speed of light, all your velocity would be in the spatial direction and none in the temporal direction. Time would completely stop for you. But because you have mass, you can never completely redistribute your velocity in this way. You must always have some velocity in the temporal direction. Massless photons can have all their velocity in the spatial direction. That is why they do not experience time. That is why, from their perspective, the universe is completely contracted. They have no temporal direction at all. This is the deep, fundamental reason for the speed limit of light. It is not an arbitrary restriction. It is a consequence of the geometry of space-time. It is like asking, why can't you go further north than the North Pole? It is not that there is a wall there. It is that further north ceases to have meaning. Similarly, faster than c ceases to have meaning in the framework of relativity. It is not that there is a wall stopping you. It is that you have redistributed all your velocity from time to space, and there is no more velocity to redistribute. All this is encoded in E equals mc squared. Mass is energy. Energy increases with velocity. Velocity approaches c, but never reaches it. Everything is connected in a perfect network of mathematics that describes the fundamental structure of the universe. So, when you ask, why can I not travel faster than the speed of light? The answer is not because you do not have enough fuel. The answer is because you have mass. And having mass means you must always experience time, and experiencing time means you cannot redirect all your velocity into space. It is a geometrical impossibility, as fundamental as asking why 2 plus 2 cannot be 5. And this leads us to the deepest question of all. If c is not really the speed of light, what is it? What does it truly limit? Here is the truth that will completely change your understanding of the universe. c is not the speed of light. It never was. Light simply travels at that speed because it has no other choice. But c is something much more fundamental. It is the speed of causality. It is the speed of information. It is the speed of the universe itself. For more than a century, we have been calling it the speed of light, because light was the first thing we measured traveling at that speed. But that is like calling water the substance that boils at 100 degrees. Technically correct, but it completely misses the point of what water really is. So, what is c, really? It is the maximum speed at which any causal influence can propagate in the universe. It is the speed at which information travels from one place to another. It is the speed of space-time itself. Let me explain what this means. Imagine you are floating in space and you wave your hand. That action, that movement, creates a perturbation in the space-time around you, and that perturbation propagates outward like ripples in a pond. But those ripples do not propagate instantaneously. They propagate at a maximum speed, and that speed is c. Now, when you wave your hand, you are also creating gravitational waves, ripples, in the very fabric of space-time. These waves were predicted by Einstein in 1916 as part of his theory of general relativity, but they were not directly detected until September 14, 2015, when the LIGO detectors captured the gravitational waves from two black holes that collided 1.3 billion light-years away. And do you know what speed those gravitational waves travel? Exactly. c, the same speed as light. Not because gravity is somehow similar to electromagnetic light, but because both are manifestations of the same fundamental limit, the speed of causality. In fact, all massless particles travel at c, the photons that transmit the electromagnetic force, the hypothetical gravitons that would transmit gravity, the gluons that transmit the strong nuclear force, all travel at c. And there is something more profound here. Information itself cannot travel faster than c. No matter what method you use, no matter what technology you invent, information has a speed limit, and that limit is c. Why? Because if information could travel faster than c, you could violate causality. You could make effects precede causes. You could, in principle, send information to the past, and that would create impossible logical paradoxes. Imagine you could send a faster-than-light signal from Earth to a spaceship moving away from you. Due to the relativity of simultaneity that we discussed before, there is a frame of reference in which that signal travels backward in time. The ship could then send a signal back to Earth, also faster than light, and from certain frames of reference, that signal would also travel backward in time. The result is that you could receive a response before sending the original message. You could receive information about the future. You could create causal paradoxes, like the famous grandfather paradox. The universe avoids these paradoxes by making it impossible for anything, including information, to travel faster than c. It is not just a convenient rule. It is a logical necessity. Causality itself depends on it. So, c is not the speed limit of physical objects moving through space. It is the speed limit of causal influence. It is the speed at which causes to propagate, to create effects. This has profound implications. It means the universe has a causal horizon. If a star explodes 1,000 light-years away, we cannot know it until the light from the explosion reaches us 1,000 years later. During those 1,000 years, that explosion does not exist for us. It cannot affect us in any way. It is outside our past light cone. Similarly, there are parts of the universe that we can never observe, no matter how long we wait. Due to the expansion of the universe, there are galaxies so distant that their light will never reach us. They are outside our causal horizon. For all practical purposes, they do not exist in our observable universe. And here is the really strange part. c not only is the speed limit of moving things, but it also defines the structure of space-time itself. In relativity, we do not think of space and time as separate things. We think of space-time as a single, four-dimensional entity, and the geometry of that space-time is not Euclidean. It is not like the flat geometry you learned in school. It is a hyperbolic geometry, where time and space are mixed in a strange way. And what mixes time and space, what defines the geometry of space-time, is c. It is the conversion constant between spatial dimensions and temporal dimensions. It is what makes meters and seconds comparable in the equations of relativity. In fact, physicists often work in units where c equals 1. In these units, a distance of 300 million meters is the same as a time of 1 second. Space and time become interchangeable, and c is simply the conversion constant between them. But there is even more. c also appears in Maxwell's equations of electromagnetism. In fact, Maxwell was the first to realize that the speed of light could be calculated from electromagnetic constants. The equation is c equals 1 over the square root of the product of epsilon 0 and mu 0, where epsilon 0 is the permittivity of the vacuum and mu 0 is the permeability of the vacuum. These are properties of the vacuum itself, of empty space. And when you take the inverse of the square root of their product, you get exactly 300,000 kilometers per second. This means that c is not just a speed that we measure. It is something that emerges from the properties of the vacuum itself. It is woven into the structure of empty space. It is a property of the universe at its most fundamental level. And here is the final revelation. All the fundamental forces of nature, all interactions between particles, propagate at c. The electromagnetic force propagates through photons that travel at c. The hypothetical gravitons that would transmit gravity travel at c. The gluons that transmit the strong nuclear force travel at c. Only forces that involve massive particles, like the weak nuclear force, which involves $W and $Z bosons, propagate slower than c. But that is only because the force carriers have mass. The underlying information, the underlying causal influence, is still limited by c. So, when we ask, why can nothing go faster than the speed of light, we are asking the wrong question. The correct question is, why does causality have a maximum speed? And the answer is, because space-time has a specific geometry, a specific structure that emerges from the fundamental properties of the vacuum. C is the constant that defines that structure. It is not an arbitrary speed limit imposed from outside. It is an intrinsic property of the fabric of the universe. And this leads to an even deeper realization. Light is not special because it travels at c. Light travels at c because it has no mass. And everything that has no mass must travel at the speed of causality, at the speed of space-time itself. If we discovered tomorrow that photons have a minuscule mass, then they would no longer travel at exactly c. They would travel slightly slower, but c would still be the fundamental speed limit of the universe. It would still be the speed of causality, only it would no longer be the speed of light. In fact, for years, physicists thought that neutrinos were massless and traveled at c. But in 1998, we discovered that neutrinos do have mass, although extremely small. That means they travel slightly slower than c, though the difference is so minuscule that it is almost impossible to measure. But c did not change. C is still c, because c was never about light or neutrinos or any specific particle. It was always about the structure of space-time. So, we should stop calling it the speed of light and start calling it the speed of causality. It would probably be more accurate, but the name has stuck, and as long as we understand what c truly represents, the name is just a detail. What matters is this: c is the most fundamental constant of the universe. It is not just a number we measure, it is a property that emerges from the structure of reality itself. It is the speed at which information propagates. It is the speed of space-time. It is the speed limit of causality itself. And once you understand this, you start seeing c everywhere. In E equals mc squared, in Maxwell's equations, in Einstein's field equations, in relativistic quantum mechanics. It is woven into every fundamental equation of physics, because c is not a constant that we add to our theories. It is the constant around which our theories are built. It is the thread that connects space to time, mass to energy, cause to effect. It is the speed of the universe. And now that you know this, you will never see light the same way again. Now that you understand that c is the fundamental speed limit of the universe, the speed of causality itself, you are probably thinking, but wait, I have heard that there are things that travel faster than light. And you are right. You have heard that because the internet is full of sensational headlines about things that break Einstein's speed limit. But here is the truth. None of those things actually violate relativity. Each one is a misunderstanding of what c actually limits. So, let us examine the most common apparent exceptions and see why they are not really exceptions at all. Apparent exceptions to the cosmic speed limit. We begin with the most dramatic, the expansion of the universe. The universe is expanding. Not only that, it is expanding faster and faster. Distant galaxies are moving away from us at speeds that appear to exceed the speed of light. In fact, there are galaxies so distant that they are receding from us faster than c, much faster. Some galaxies at the edge of our observable universe are moving away at speeds that are several times the speed of light. So, does this not violate relativity? Did we not just say that nothing can move faster than c? The answer is no, and the reason is subtle, but crucial. Those galaxies are not moving through space faster than light. The space itself between us and them is expanding, and there is no speed limit for the expansion of space. Imagine you draw two dots on a deflated balloon, and then you inflate the balloon. The dots move away from each other, but neither dot is moving on the surface of the balloon. The surface itself is stretching. Similarly, the galaxies are not moving through space. The space between them is expanding. Relativity says that nothing can move through space faster than c, but it says nothing about how fast space itself can expand. In fact, during the first instance after the Big Bang, in a period called cosmic inflation, space expanded exponentially, much faster than the speed of light. Regions that were causally connected separated faster than c, and that is okay, because information still does not travel faster than c. A galaxy that is receding from us, faster than the speed of light, is outside our causal horizon. We cannot send a signal to it. We cannot receive information from it. For all practical purposes, it is outside our universe. The speed limit c is a local limit. It applies to objects moving through space. It does not apply to the expansion of space itself. Now let us talk about the second most common exception, quantum entanglement. In quantum mechanics, two particles can be entangled in such a way that measuring one instantly affects the other, no matter how far apart they are separated. Einstein famously called this spooky action at a distance, and used it as an argument that quantum mechanics must be incomplete, but experiments have repeatedly shown that quantum entanglement is real. If you have two entangled electrons, and you measure the spin of one on Earth, you instantly know the spin of the other on Mars. There is no delay. It is instantaneous, faster than light, much faster. So, does this violate relativity? Again, no, because even though the correlation is instantaneous, no information is transmitted. This is the crucial part that most popular explanations miss. When you measure the spin of the first electron, you get a random result, up or down, with 50% probability each. You now know that the other electron will have the opposite spin, but that information only exists for you after the measurement, and to communicate that information to someone on Mars, you still have to send a classical signal that travels at c or slower. The person on Mars measuring their electron also gets random results, 50-50, up or down. Only when they compare their results with yours, traveling at c or slower, can they see the correlation. You cannot use quantum entanglement to send a message. You cannot control what result you get in your measurement, so you cannot encode information. The correlation is there, but it does not transmit usable information. And remember, c is the speed limit of information, of causal influence. Quantum entanglement transmits none, so it does not violate relativity. Third exception, scissors. Yes, scissors. Imagine you have gigantic scissors with blades, 1 light-year long. You close the scissors at your end. The point where the blades meet travels towards the distant end. If you close the scissors fast enough, that point of intersection could move faster than light. Or imagine you point a very powerful laser at the moon and move it quickly. The laser spot on the moon's surface moves. If you move the laser fast enough, the spot could traverse the moon faster than the speed of light. Violations of relativity? No, because in both cases, nothing physical is traveling faster than c. In the case of the scissors, when you close your end, a pressure wave is sent along the blades towards the other end. That wave travels at the speed of sound in the scissor material, much slower than c. The point of intersection may move faster than c, but it is not a physical object. It is just a geometrical point. Similarly, the laser spot on the moon can move faster than c, but the individual photons of the laser still travel at exactly c. The spot is just where different photons strike at different times. There is no physical object moving from one side of the moon to the other. It is like when you do a wave in a stadium. The wave can travel around the stadium faster than any person can run, but no person is traveling around the stadium. They are just raising and lowering their arms in sequence. The wave is a pattern, not an object. These are examples of phase velocities, or group velocities, that can exceed c without violating relativity, because they do not involve the transport of information or energy. Fourth exception: warp drives. Science fiction is full of ships that have warp drives or hyperspace engines that allow them to travel faster than light. Star Trek, Star Wars, almost every space science fiction franchise uses them. Are they physically possible? Well, it depends on what you mean by possible. In 1994, physicist Miguel Alcubierre proposed a theoretical mechanism for faster-than-light travel that does not violate relativity. The idea is that you do not move the ship faster than c. Instead, you compress the space in front of the ship and expand the space behind it. The ship is in a bubble of normal space-time, and that bubble moves. From the perspective of someone outside the bubble, the ship appears to move faster than light. But from the perspective of someone in the ship, they are stationary in their local bubble of space-time. The space is moving, not the ship. This is mathematically consistent with relativity. Einstein's equations allow this type of space-time geometry. The problem is the energy required. Alcubierre's original calculations showed that you would need an amount of energy equivalent to the mass energy of Jupiter, and that in the form of negative energy, an exotic type of energy that may not exist in the universe. Later versions of the idea have reduced the energy requirements, but they are still astronomical. Furthermore, there are causal problems. If you could create a warp drive, you could use it to travel backward in time in certain frames of reference, creating temporal paradoxes. So, is it possible? Perhaps technically, but it is so improbable and problematic that most physicists consider it pure science fiction. Fifth exception: superluminal speed in media. Light travels at c in a vacuum, but when light travels through materials like water or glass, it slows down. In water, light travels approximately 75% of c. In diamond, around 40% of c. This creates an interesting possibility. If you have a charged particle moving through water faster than light travels in water, although still slower than c in a vacuum, it creates an effect called Cherenkov radiation. It is the optical equivalent of a sonic boom, a cone of blue light that trails behind the particle. This is real and commonly observed in nuclear reactors, where high-energy particles travel through the reactor water faster than light in the water. The characteristic blue glow of nuclear reactors is Cherenkov radiation. But is this faster than light? No, not really. The particle still travels slower than c in a vacuum. It is only faster than light in a specific medium. The fundamental limit c is never violated. Sixth and final exception: tachyons. Tachyons are hypothetical particles that always travel faster than light. They were proposed as a mathematical curiosity. If the equations of relativity allow particles that never go slower than c, like photons, do they allow particles that never go slower than c? Mathematically, yes. If a particle had imaginary mass in the mathematical sense of a number involving the square root of -1, then the equations of relativity would say that it always travels faster than c, and that decelerating to c would require an infinite energy, exactly the reverse of normal particles. But there are huge problems with tachyons. They would violate causality. They could travel backward in time. They would create impossible logical paradoxes. And most importantly, we have never detected one. Not even a hint of evidence that they exist. Most physicists consider tachyons to be just mathematical curiosities, artifacts of the equations that do not correspond to anything in physical reality. So, what is the conclusion? Every apparent exception to the speed limit c either does not actually violate relativity when you understand it correctly, or is so speculative and problematic that it is probably not physically real. The expansion of space is not movement through space. Quantum entanglement does not transmit information. Geometric points and patterns are not physical objects. Warp drives require exotic physics that probably do not exist. Speed in media is not the same as speed in a vacuum, and tachyons probably do not exist. The speed limit c holds. There is no escape, No trick, no exception. It is a fundamental law of the universe, woven into the very structure of space-time. And now that we have ruled out the exceptions, we can ask the deepest question of all. Why? Why does the universe have this specific limit? Where does that number come from? And what would happen if it were different? We have established that C is fundamental, that it is not arbitrary, that it is woven into the very structure of the universe. But now comes the question that should be burning you. Why exactly 299,792,458 meters per second? Why not double? Why not half? Who or what decided that specific number? The answer is one of the most beautiful revelations in physics. No one decided. The number emerges naturally from the electromagnetic properties of the vacuum, and those properties, in turn, are connected to the fundamental geometry of spacetime. Let us start with James Clerk Maxwell. In the 1860s, Maxwell unified all known electrical and magnetic phenomena into an elegant set of 4 equations. These equations, now called Maxwell's equations, describe how electric and magnetic fields are created, how they interact with each other, and how they propagate through space. And when Maxwell solved his equations to see how an electromagnetic wave would behave, something extraordinary happened. The speed of that wave emerged directly from the equations. He did not have to put it there. It was not an adjustable parameter. It came out automatically from the mathematics, and the speed was c equals 1 over the square root of the product of epsilon 0 and mu 0. Here, epsilon 0 is the electric permittivity of the vacuum, which measures how easily electric fields form in empty space. Mu 0 is the magnetic permeability of the vacuum, which measures how easily magnetic fields form in empty space. These are properties of the vacuum itself, of empty space, and when you take the inverse of the square root of their product, you get exactly 300,000 kilometers per second. Maxwell did this calculation in 1862 and realized something astonishing. The speed of the electromagnetic waves that his equations predicted was the same as the measured speed of light. Not similar, identical, within the margin of experimental error. This could not be a coincidence. Maxwell concluded that light itself was an electromagnetic wave, and with that, he unified optics with electromagnetism. Light, electricity, and magnetism were all manifestations of the same fundamental phenomenon. But there is something deeper here. Why do epsilon 0 and mu 0 have the values they have? Are they arbitrary? Could a different universe have different values? The short answer is yes, they could be different. But if they were, C would be different. And if C were different, everything would be different. You see, epsilon 0 and mu 0 are not really independent. They are connected through Maxwell's equations, and both are connected to other fundamental constants of physics. They are all interwoven in a network of mathematical relationships. For example, the fine structure constant, represented by alpha, is a dimensionless number that characterizes the strength of the electromagnetic interaction. Its value is approximately 1 over 102.37, and it is related to epsilon 0, the charge of the electron, and Planck's constant. If you changed epsilon 0, you would have to change alpha, and if you changed alpha, you would change the strength of all electromagnetic interactions in the universe. Atoms would behave differently. Chemistry would be different. Stars would function differently. In fact, there is an entire area of physics called cosmological fine-tuning that studies exactly this. Physicists have calculated what would happen if the fundamental constants of the universe were slightly different, and the answer, over and over again, is everything would fall apart. If C were 10% greater, the electromagnetic forces would be different. Atoms would not form the way they do. If it were 10% less, the same. The range of values of C that allows chemistry, and therefore life, to exist is surprisingly narrow. But there is an even deeper level of explanation. Why does space-time have the geometry it has? Why 3 spatial dimensions and 1 temporal dimension? Why the Minkowski metric that combines space and time in that specific way? The honest answer is, we do not fully know, but we can explore the consequences of that geometry. In the Minkowski space-time geometry, which is the geometry of special relativity, space and time are not combined in the way you might expect. In normal Euclidean geometry, the distance between 2 points is given by the square of the distance equals the square of the $x, dollar component, plus the square of the $y, dollar component, plus the square of the $z, dollar component. But in Minkowski spacetime, the interval between two events is the square of the interval equals the square of c multiplied by the square of the time component minus the square of the $x, dollar component, minus the square of the $y, dollar component, minus the square of the $z, dollar component. Note the negative sign. Time enters with an opposite sign to space. That is the signature of spacetime geometry. And that factor of c squared is there to convert time into the same units as space. This geometry has profound consequences. It means that you can trade space for time. By moving faster through space, you move slower through time. There is a trade-off, and the conversion factor is c. In fact, in modern physics, especially in relativity, we often measure time in meters. 1 second is 300 million meters, the distance that light travels in 1 second. This may seem strange, but it makes the equations much simpler and reveals the fundamental symmetry between space and time. In these units where c equals 1, the equations of relativity become much more elegant. $E equals $mc. $2 becomes simply $E equals $m. Mass and energy are literally the same thing, with the same number. The distinction between them disappears, and the speed limit c becomes simply the speed limit 1. You cannot go faster than 1. What does that mean? It means you are using all your velocity through time to move through space. There is no more velocity to redistribute. This is the hidden geometry of spacetime. C is not just a number we measure. It is the fundamental conversion constant between the spatial dimensions and the temporal dimension. It is what makes spacetime be spacetime instead of separate space and time. And there is another profound connection. In string theory, one of the leading candidates for a unified theory of all physics, spacetime emerges from interactions of vibrating strings in higher dimensions, and C emerges naturally from those interactions. It is not something you put into the theory, it is something that comes out of it. Similarly, in loop quantum gravity, another approach to fundamental physics, spacetime itself is quantized, made of tiny atoms of spacetime, and C emerges from the properties of those fundamental atoms. Therefore, in the deepest theories of physics, C is not a constant you need to explain. It is a consequence of the fundamental structure of reality. It is like asking why pi is approximately 3.14. It is not that someone decided that value. It is that is how the geometry of circles works. Similarly, C is that way because that is how the geometry of spacetime works. But there is an even more surprising connection. In 1998, physicists discovered that the expansion of the universe is accelerating. There is a mysterious form of energy called dark energy that is driving this acceleration, and the density of dark energy is related to something called the cosmological constant. The cosmological constant has dimensions of 1 over length squared, and when you convert it to standard units, it involves c. Dark energy is connected with c in ways we are only beginning to understand. Some physicists speculate that c itself might not be constant. Perhaps in the very early universe, c was different. Perhaps it is changing very slowly over time. If so, we would measure subtle effects in atomic physics and cosmology. But so far, all tests show that c is constant, with extraordinary precision. Yet, the idea of a variable c remains an intriguing theoretical possibility. And there is another fascinating connection. In quantum mechanics, there is another fundamental constant, Planck's constant, represented by h. This constant sets the scale of quantum phenomena, and it turns out that h and c together define what are called the Planck length, the Planck time, and the Planck energy. The Planck length is approximately 10 to the negative 35 meters. It is the smallest scale of length that has physical meaning. Below that scale, space-time itself becomes foamy and quantum. The Planck time is approximately 10 to the negative 44 seconds. It is the shortest time that has physical meaning, and these Planck scales are defined by combinations of c, h, and the gravitational constant g, the three fundamental constants of the universe, intertwined to define the fundamental scales of reality. So, when you ask where c comes from, the answer is that it emerges from the geometry of spacetime, from the electromagnetic properties of the vacuum, and from the fundamental scales of quantum physics and gravity. It is not a free parameter you can adjust. It is a consequence of how the universe is constructed at its most fundamental level. And that is the profound beauty of c. It is not an arbitrary number that someone wrote into the equations. It is a number that emerges inevitably from the mathematical structure of reality. It is, as physicists say, a result, not an assumption. And once you see it that way, you begin to appreciate that we live in a universe with a very specific, very special geometry. A geometry that allows causality, that allows stable structures, that allows information to exist, that allows us to exist. And c is the constant that defines that geometry. It is the thread that connects everything. And now that you understand it, we can explore what would happen if it were different. Thought experiments are one of the most powerful tools in physics. Einstein used them to develop relativity. Now we are going to use one to explore one of the deepest questions about our universe. What would happen if c, the speed of light, were different? We are not talking about changing it slightly. We are talking about imagining alternative universes where c is double or half or 10 times greater or smaller. What would happen to physics, chemistry, and life? Would we still exist? The short answer is no, almost certainly not. But the why reveals profound truths about the fine-tuned nature of our universe. Let us start with a universe where c is much slower, say 1,000 meters per second. That is approximately 3 times the speed of sound. In that universe, you could see relativistic effects in your daily life. If you drive your car at 100 kilometers per hour, you would be traveling at 10% of that universe's speed of light. Your time would dilate measurably, your mass would increase. You could literally see objects contract when they pass quickly. Stars would appear blue, shifted in front of you, and red shifted behind you, due to the relativistic Doppler effect. It sounds interesting, right? But there is a problem, a huge problem. Remember that c is related to the electromagnetic properties of the vacuum through the equation. c equals 1 over the square root of the product of epsilon 0 and mu 0. If c is slower, then epsilon 0 or mu 0 or both must be different. And if those constants are different, all of electromagnetism changes. Atoms would not behave the same way. The electromagnetic force between the electron and the proton in a hydrogen atom depends on epsilon 0. If you change epsilon 0, you change that force. Electrons would orbit at different distances. The energy levels would be different. Chemistry would be completely different. But it gets worse. E equals mc squared tells us that mass and energy are interchangeable with c squared as the conversion factor. If c is 1,000 meters per second instead of 300 million, then c squared is 1 million instead of 90 quadrillion. That means the amount of energy contained in mass is 90 billion times less. The nuclear reactions that power the sun depend on converting mass into energy. If c were much smaller, those reactions would release vastly less energy. The sun could not shine the way it does. In fact, it probably could not exist as a stable star at all. And here is the real problem. Atoms themselves are stable due to a delicate balance of forces. the electromagnetic force that attracts electrons to the nucleus, quantum mechanics that prevents electrons from falling into the nucleus, and the strong nuclear force that holds the nucleus together, despite the electromagnetic repulsion between protons. All these forces are connected with C in subtle ways. The fine structure constant that determines the strength of the electromagnetic interaction involves C. The masses of the particles that determine how they behave under the strong nuclear force are related to C through E equals mc squared. If you change C significantly, this entire balance falls apart. Atoms would not be stable. You could not have complex molecules. You could not have chemistry. You could not have life. Now, let us consider the other extreme. What if C were much faster, say 10 times faster than in our universe? With a faster C, relativistic effects would be even harder to detect in daily life. You would have to travel much faster to notice time dilation or mass increase. In that sense, it would be more like common sense Newtonian physics. But again, there are profound problems. If C is greater, then C squared is much greater. That means the amount of energy contained in mass is much greater. A small amount of mass would release devastating amounts of energy. Nuclear reactions in stars would be much more violent. Stars would burn their fuel much faster. Instead of shining stably for billions of years, they might explode in a matter of millennia, or even centuries, and the balance of forces in atoms would change again. With a different C, the fine structure constant would be different. Atomic energy levels would change. Molecular bond lengths would change. All chemistry would be different. There are detailed calculations that show that if you change C by more than a few percent, the range of stellar masses that allows stable, long-lived stars like the Sun disappears. Either all stars would be too massive and live short, violent lives, or they would be too small and never ignite nuclear fusion. Without stable, long-lived stars, there is no time for life to evolve. Without stable chemistry, there are no complex organic molecules. Without stable atoms, there is no chemistry at all. This is the anthropic principle in action. The fundamental constants of the universe, including C, appear to be fine-tuned to allow the existence of complex structures and ultimately, life. Change any of them significantly, and the universe becomes barren, inhospitable to anything remotely like us. Some physicists find this deeply unsettling. Why are the constants tuned to just the right values? Is it coincidence, design, or is there a deeper explanation? One possible answer is the multiverse. If infinite universes exist with different values for the fundamental constants, then we would naturally find ourselves in one of the rare universes where the constants allow life to exist, not because our universe is special, but because we can only exist in universes that permit life. It is a selection bias. Another possible answer is that the constants are not really independent. Perhaps they are all connected by a deeper theory that we have not yet discovered. String theory, for example, suggests that all fundamental constants emerge from the geometry of additional dimensions. In that case, the values are not arbitrary. They are inevitable consequences of the fundamental structure of reality. But there is another fascinating aspect of the fine-tuning of C. It is not just that C has to be in a narrow range. It is that C is exactly the right constant to connect all the other constants coherently. Think about it. C appears in E equals mc squared, connecting mass and energy. It appears in Maxwell's equations, connecting electricity and magnetism. It appears in the Lorentz transformations, connecting space and time. It appears in the fine structure constant, connecting quantum mechanics with electromagnetism. It appears in the Planck scales, connecting quantum mechanics with gravity. It is as if C is the central piece of a cosmic puzzle. Changing it would break all these connections. The universe would lose its mathematical coherence, and there is experimental evidence of this fine-tuning. Physicists have measured the fundamental constants with extraordinary precision, and they have searched for variations in those constants over cosmic time, by observing the light from distant galaxies, looking at the universe as it was billions of years ago. So far, the constants appear to be truly constant. C was the same 10 billion years ago as it is now, with a precision of 1 part in a million. The fine structure constant was the same, with similar precision. The universe has maintained its fundamental constants through almost all of its history. This is remarkable. It means that the fine-tuning is not just a coincidence of the current universe. It is a property that has persisted through almost 14 billion years of cosmic evolution. Some physicists have proposed that the constants might have been different in the very early universe, immediately after the Big Bang. During the era of inflation, when the universe expanded exponentially, the constants might have frozen into their current values. Different regions of the universe might have frozen different values, creating a multiverse of varied constants. But in our observable region of the universe, C is what it is, and that value allows atoms, molecules, stars, planets, and life to exist. There is another fascinating angle. Some physicists have calculated what would happen if not only C were different, but multiple constants simultaneously. It turns out there are trade-offs. If you change C, but also change another constant in the right way, you could keep the universe habitable. For example, if you increase C, but simultaneously decrease the fine structure constant in the correct proportion, you could maintain stable chemistry. There is a parameter space of allowed values, not just a single point, but that parameter space is extremely small compared to all possible values. It is like saying there is a small range of temperatures where water is liquid, but compared to all possible temperatures from absolute zero to infinity, that range is minuscule. So, what does all this tell us? It tells us that we live in an extraordinarily special universe. The fundamental constants, including C, are precisely tuned to allow complexity, structure, chemistry, and life. Change any of them significantly, and everything falls apart. Is this evidence of design, of multiverses, or of a deeper theory yet to be discovered? We do not know. But what we do know is that we should not take our universe for granted. It is a special place, governed by laws that allow everything we know and love to exist. And at the heart of those laws is C, the constant that connects space to time, mass to energy, and cause to effect. It is not just a speed limit, it is the signature of the universe, the constant that defines everything. For more than a century, C has reigned as the fundamental speed limit of the universe, but in recent years, physicists have begun to discover that C might not be the only fundamental limit. There are other limits, just as profound, just as unbreakable, that govern what is possible in our cosmos. These limits are not about speed. They are about complexity, information, and the growth of physical processes. And they are starting to change our understanding of what a limit in physics really is. Let us start with the most recent and fascinating work. The research of Toby Ord from the University of Oxford, published in 2024. Ord was studying something called the busy beaver function, a concept from computer science theory. Without going into complex technical details, the busy beaver function asks, what is the largest number that a computer can calculate with a given number of instructions before stopping? The strange thing is that this function grows incredibly fast, faster than exponential, faster than any function you can imagine. In fact, it grows so fast that it eventually surpasses any possible physical process in the universe. Ord realized that this creates a fundamental physical limit. There is a point where the busy beaver function grows faster than the universe can physically support. You cannot build a computer that calculates busy beaver values past a certain point, because there is literally not enough energy, space, or time in the universe to do it. This is a different kind of limit than C. It is not about speed, it is about computational complexity, but it is just as fundamental. It says there is a maximum limit to the growth of physical processes, no matter how much energy or resources you have. And this connects to something deeper. The idea that the universe itself is, in a sense, a computer, not a computer designed by someone, but that it literally processes information through the laws of physics. Every particle interaction is a computational operation. Every physical transformation is a calculation. If that is true, then the universe has computational limits. There is a maximum number of operations the universe can perform. There is a maximum amount of information it can store. These limits emerge from Planck's constant, the gravitational constant, and the fundamental properties of space-time. Physicist Seth Lloyd from MIT has calculated exactly these limits. According to his calculations, based on known physics, the observable universe has performed approximately 10 to the power of 120 operations since the Big Bang, and contains approximately 10 to the power of 90 bits of information. These are huge, almost incomprehensible numbers, but they are finite. The universe has a computational budget. It cannot perform infinite calculations. It cannot store infinite information. And here is the connection with c. The speed of light determines how fast information can propagate. Combined with the finite age of the universe, this creates a computational horizon. There are calculations that are physically impossible, not because they require too much energy, but because they require more time than the universe has existed, even in principle. But there is another, even more fundamental limit, the Bekenstein bound. In the 1970s, physicist Jacob Bekenstein demonstrated something extraordinary. There is a maximum amount of information that can be contained in any region of space. No matter how many particles you pack in there, no matter how you organize things, there is an absolute limit. And that limit depends on the area of the region, not its volume. This is profoundly strange. Normally, you would think that the amount of information you can store depends on the volume, on how much space you have. But Bekenstein showed that it depends on the surface area. The formula is, the maximum number of bits of information is proportional to the surface area divided by the Planck length squared. And the Planck length is defined by c, Planck's constant h, and the gravitational constant g. So, c is directly involved in determining how much information can exist in any region of space. It is another fundamental limit, just as unbreakable as the speed limit. Why does this limit exist? Because if you try to pack more information, the energy density becomes so high that it collapses into a black hole. And once you have a black hole, the information is trapped behind the event horizon. You cannot access it. It has effectively disappeared from the observable universe. This leads to something called the holographic principle, one of the most radical ideas in modern physics. The holographic principle says that all the information contained in a volume of space can be described by information on the surface of that volume. The three-dimensional universe we experience could be, in a sense, a projection of information encoded on a two-dimensional surface. If this is true, then the universe has properties similar to a hologram, and C is at the center of this idea because it determines how the information on the surface relates to the processes in the volume. There is another fascinating limit related to time. It is called the Margolis-Levitin limit, named after physicists Norman Margolis and Lev Levitin, who discovered it in 1998. This limit says that there is a maximum speed at which a physical system can change state. No matter how much energy you give it, no matter how you configure it, there is a maximum rate of change, and it is determined by the system's energy and Planck's constant. The formula is, the minimum time for a state change is proportional to Planck's constant divided by the energy. And again, this connects to C through E equals mc squared. This limit means that the universe has a maximum refresh rate. If you think of the universe as a simulation, it cannot update faster than this limit. It is not that the universe is literally a simulation, but that there are fundamental physical limits on how fast things can happen. Combining the Margolis-Levitin limit with the Bekenstein bound, you get limits on the ultimate computational capacity of the universe. Lloyd and others have calculated that even if you converted all the mass energy of the observable universe into the most physically efficient computer possible, operating at the Margulis-Levitin limit, storing information at the Bekenstein bound, there would still be calculations you could not perform in the age of the universe. There are mathematical problems whose solutions are physically out of reach, not due to technological limitations, but due to fundamental limitations of physics. And all these limits are connected with c, because c is the constant that relates space to time, mass to energy, and information to physics. It is the thread that weaves all these limits together. But there is an even deeper limit that physicists are just beginning to explore: the limit on predictability. Quantum mechanics tells us that the universe is fundamentally probabilistic. You cannot predict with absolute certainty what will happen, only the probabilities of different outcomes. But there is a deeper question. Are there events that are fundamentally unpredictable, even in principle, even with complete knowledge of all initial conditions? The answer seems to be yes. Chaos theory tells us that some systems are extremely sensitive to initial conditions. The classic example is the butterfly effect. A butterfly flapping its wings in Brazil could in principle cause a tornado in Texas weeks later. But in quantum reality, you cannot measure initial conditions with infinite precision. Heisenberg's uncertainty principle forbids it. Combining quantum uncertainty with deterministic chaos, you get a fundamental unpredictability, and there is a predictability horizon, a time beyond which, even with the best possible computer, you cannot make reliable predictions. This horizon depends on c, on Planck's constant, on the nature of the system you are trying to predict. For some systems, like the weather, the predictability horizon is days or weeks. For others, like the orbit of Pluto, it is millions of years. But for all systems, there is a horizon. Beyond it, the future is fundamental unknown. So, c is not just a speed limit. It is part of a network of limits that define what is possible in our universe. Limits on speed, limits on information, limits on computational complexity, limits on predictability. These limits are not arbitrary restrictions. They are consequences of the fundamental structure of space-time, of quantum mechanics, and of the nature of information and causality. And they are all connected. Change one, and you change all the others. They are part of a coherent package of physical laws that define what is and what is not possible. Some people find these limits depressing. It means there are things we will never know, places we will never reach, problems we will never solve. The universe has fundamental barriers, and there is no way to overcome them, but there is another way to see it. These limits are what makes the universe comprehensible. Without limits, anything would be possible, and nothing would have meaning. Limits create structure, create order, and create the conditions for complexity to exist. C and the other fundamental limits are not restrictions on what the universe can be. They are the rules that allow the universe to be something at all. And there is beauty in that. Beauty in the economy of the laws of physics. Beauty in how all these limits connect with each other. Beauty in how they emerge from simple and profound principles. We live in a universe with limits, but those limits are what make it real, what make it coherent, what makes it our home. We have reached the end of our journey through the limits of the universe. We have explored the history of how we discovered c. We have unraveled why nothing with mass can reach it. We have revealed that c is not really the speed of light, but the speed of causality itself. We have examined the apparent exceptions that are not really exceptions. We have explored where that specific number emerges from, and what would happen if it were different. And we have discovered that c is just one of multiple fundamental limits that define our universe. But now comes the final revelation, the deepest truth of all. A truth so strange, so counterintuitive, that even after explaining it, your mind will struggle to fully accept it. You are traveling at the speed of light right now, not through space, but through space-time. Let me explain what this means. In relativity, space and time are not separate entities. They are part of a unified four-dimensional construct called space-time. 3 dimensions are spatial: up, down, left, right, forward, back. One dimension is temporal past, future. And in this four-dimensional space-time, everything moves at exactly the same speed. C, the speed of light. But wait, you might say, I am sitting still. I am not moving at all. And you are right, you are not moving through space, but you are moving through time. Every second that passes, you move 1 second into the future. That is movement through the temporal dimension. And it turns out that this movement through time is, in a profound sense, the same as movement through space. They are components of the same kind of movement through space-time. Imagine you have a fixed velocity through space-time, and that velocity is c. You can distribute that velocity between the spatial dimensions and the temporal dimension, but the total amount is always c. When you are at rest, all your velocity is in the temporal direction. You are moving through time at the maximum speed, c. You are traveling into the future at 1 second per second. That is the speed of light through time. When you start moving through space, some of your temporal velocity is converted into spatial velocity. It is as if your total velocity is a vector that can point in different directions in space-time. When you rotate it towards the spatial dimensions, it moves away from the temporal dimension. And here is the crucial part. The more spatial velocity you have, the less temporal velocity you have. Movement through space steals movement through time. That is why time slows down when you move fast. It is not magic, it is geometry. If you travel in a spaceship at 90% of c through space, your velocity through time is reduced. Your clock runs slower. You experience less time per kilometer traveled. You have redistributed your velocity from the temporal dimension towards the spatial dimensions. And if you could reach exactly c through space, something impossible, if you have mass, then all your velocity would be in the spatial dimensions. You would have no velocity through time. Time would completely stop for you. This is exactly what happens to photons. All their velocity is in the spatial dimensions. They have no velocity through the temporal dimension. That is why, from a photon's perspective, no time elapses. It is emitted by a star and absorbed by your eye instantaneously from its point of view, even if the journey took 1,000 years from our perspective. This is the profound symmetry between space and time in relativity. They are not fundamentally different things. They are different aspects of the same space-time, and movement through them is connected by c. In physics, this is described using something called the four-velocity vector. Your ordinary velocity is a three-dimensional vector that points in the direction you are moving, but your four-velocity vector also includes your velocity through time, and the magnitude of that four-velocity vector, its length in four-dimensional space-time, is always exactly c for everyone, all the time, without exception. This means that the question, why can I not go faster than the speed of light, is poorly formulated. The correct question is, why can I not redistribute all my velocity from time to space? And the answer is, because you have mass. And having mass means you must always have some velocity in the temporal direction. Massless particles like photons can redistribute all their velocity to space. That is why they travel at c through space and do not experience time. But you, made of massive particles, must always maintain some temporal velocity. You must always experience time. And here is the deep philosophical implication. There is no such thing as being at rest in an absolute sense. Even when you are sitting perfectly still, you are moving at c through space-time. You are moving through time at maximum velocity. Time is not something that just happens around you. It is something you move through, just as real as movement through space, and your speed through it is limited by c, exactly like your speed through space. This resolves an old paradox. People often ask, if everything is relative, why does time always move forward? Why can't we move backward in time as we can move backward in space? The answer is that there is a fundamental asymmetry between time and space. Although they are unified in space-time, they are not identical. Time enters the equations with a negative sign in the Minkowski metric. That is the mathematical signature that time is different. And that difference means that while you can change direction in space, turning your spatial velocity in any direction you wish, you cannot turn your temporal velocity backward. The arrow of time points in one direction, toward the future, always. This is connected with the second law of thermodynamics, which says that entropy always increases. The universe is moving from order toward disorder, and that process defines the arrow of time. We cannot reverse it, at least not globally. But there is something deeper here. The reason why entropy increases is connected with quantum statistics, with the probabilistic nature of reality at a fundamental level. And that, in turn, is connected with C through the Heisenberg uncertainty relations. Everything is connected. The speed limit C, the arrow of time, the second law of thermodynamics, quantum mechanics, the structure of space-time. They are different aspects of the same fundamental reality. And now, understanding all this, we can finally answer the question with which we began. Why can nothing travel faster than the speed of light? Because c is not a speed limit in the ordinary sense. It is not a barrier preventing you from going faster. It is the natural velocity of the universe. It is the speed at which everything moves through space-time. It is the speed of causality, of information, of the very structure of reality. You cannot go faster than c, for the same reason you cannot be more north than the North Pole. There is no more faster than c in space-time. You are already using all your velocity. You are already traveling at c. It is just that most of that velocity is in the temporal direction, not the spatial directions. And here is the final beauty of all this. This understanding unifies everything we have learned. Why does time dilate? Why does space contract? Why does mass increase with velocity? Why does light travel at c? Why does causality exist? Why does the universe have limits? It all comes down to the geometry of space-time, to the way space and time are intertwined, to the constant c that connects them. We live in a universe with a specific, beautiful, elegant geometry. A geometry that emerges from simple principles, but that has profound consequences. A geometry that allows structures, information, complexity, and life to exist. And c is the constant that defines that geometry. It is not arbitrary. It is not accidental. It is fundamental. It is inevitable. It is what makes the universe the universe. So, the next time you look at the night sky and see the light of the stars, remember that light has traveled for years, decades, centuries, millennia to reach you. It has traveled at c, the maximum speed of causality. And in its frame of reference, the journey was instantaneous. It experienced no time. And you, looking at that light, are also traveling at c, not through space, but through time. You are moving toward the future, at the maximum speed allowed by the universe. We are all space-time travelers, moving at c, redistributing our velocity between space and time, depending on how we move. Physics is not about restrictions. It is about possibilities, and c is the constant that defines all those possibilities. This is the final truth about the speed of light. It is not a limit that restricts us. It is the natural speed of the universe, the speed at which we all move, the constant that connects everything. And now that you know it, you will never see the universe the same way again. Every second that passes, you are traveling at 300,000 kilometers per second through time. You are a space-time traveler, navigating the geometry of the cosmos at the speed of light. Is that not extraordinary? If this journey through the limits of the universe has fascinated you, if these revelations about the nature of the reality have ignited your curiosity, then I invite you to join the Scientia Nocturna community. Here, we explore the deepest mysteries of the cosmos, those that challenge our intuition and expand our understanding, because the best questions are not the ones that have easy answers. They are the ones that force us to rethink everything we thought we knew. And the universe is full of those questions, waiting for us to discover them. Subscribe, continue the journey, because we have only just begun to unravel the secrets of the cosmos. Yeah,